I waited specially for you. It's not going to happen next week. Okay, so I hope this works. If there's any problems with the slides, apologies. I had hoped to show one or two movies that we'll have to skip, but I'll try and show those during the course instead. So, here we are. Sorry for the late start. So, lecture one, basically I'm going to try and give a tour of reinforcement learning. And the goal of this lecture is essentially to be able to understand what the rest of the course is going to be about in enough, with enough background so that you have some idea of what each of those classes will be about and what the ground is that we're covering, what reinforcement learning is, what kind of applications you can do with it, why you might be interested in this, give you some sort of overall understanding of what the key ideas are. So it's just going to be broad and shallow for this lecture. And then the remaining lectures, of course, will go individually at one topic at a time and really start to understand what this particular paradigm of machine learning is all about. Okay, so I covered some of this last time, but I just wanted to go through a couple of things which I wasn't able to cover last time, so we all know the time or we wouldn't be here. So if anyone wasn't able to write down the URL, I realise I flashed it up quite quickly, but you can find this just from my website as a teaching tab. And all information regarding this course will be placed up on this website. So when assignments become available, there'll be a link to a Google group where people can discuss issues or ask questions or can give you feedback, which is one of the reasons I'm keen to collect emails, because I know there's people here from a variety of different backgrounds actually. So it's useful just to have the link to this website, and you can contact me as well. Okay, so we've talked a little bit about assessment. Okay, I want to talk about textbooks. So somewhere in my magic bag, I have two different textbooks to discuss. So these are two different textbooks, and they're very different in their style, but they both cover most of the content, a lot of the content that we're going to discuss in this lecture. So what are the pros and cons of the two? So this book here is sort of the classic textbook that covers reinforcement learning. So this is by Sutton and Bartow, who are the founders of the field, and this is basically the textbook that everyone knows about who works with reinforcement learning. It's used by people across a wide variety of different fields as well, so it's somewhat broad. So the downside is it's getting a little bit old now, 1998, and it's a little bit longer than this other one. The good news is it's available free online from this URL, so you don't have to pay a penny to use this textbook. But it's very, very readable, and it covers a lot of the ideas, and it's a very accessible textbook, so I really recommend it. For those of you who prefer something shorter and more concise and more technical, there's this book here, which, as you can see, is very slim tome, but still covers most of the main ideas that we're going to be talking about, by Chava Sepesvari, also from these guys both from the University of Alberta, where I also did my PhD with Rich Sutton. It's really up to date. It just came out in 2010, and it's also available free online, so this is the URL. All these slides will be made available as well on the website, so the only one you really needed was the URL of the website. But some people might say this is less accessible as well, and that it's it's more technical. So for those of you who sort of natural language is more mathematical, this is probably the one to go for. And for those of you who sort of natural language is more sort of intuitive or algorithmic, then probably this is the one to read about. And the sort of presentation of material that I'll be using is probably closer to this book than to Chava's book as well. So, but with some of my own, so there'll be material which isn't quite an either, but that's okay. Okay, so reinforcement learning. So I described briefly how reinforcement learning sort of sits at the center of all these different fields, and so you can think of it as one reason why we consider it something to be interesting is when it touches on various different areas which are of interest to more than one group of people. And sometimes it's a good way to tell with your own research, is this something important? Well, will more than the group of people I immediately interact with care about this work? And the nice thing about reinforcement learning is that it impinges on all of the theory of decision making. Okay, so what makes reinforcement learning different from other machine learning paradigms? I just wanted to sort of dwell on this. I rushed through it last time. But I really just wanted to discuss this in a little bit of detail. So there's some really important distinctions. So perhaps the most important is that in reinforcement learning, like unsupervised learning, there's no supervisor. There's no one to say you're right or wrong. But in reinforcement learning, there's this very special thing which we'll talk more about, which is the reward signal, which is this feedback signal saying how well the agent's doing, good, bad, Every single time step it gets some signal saying how well it's doing. And that's quite distinct from being told at the end of the problem, look, this is how you should have solved this problem. No one's telling the agent the right way to solve the problem. It's just being told at every step how well it's doing. It has to figure out for itself through trial and error learning how to find the right solution to the problem. Another key feature of reinforcement learning compared to, say, supervised learning, which is typically, you see one example and then you get told, the supervisor tells you the correct answer. Whereas in reinforcement learning, the feedback is usually delayed. So there's no sort of instantaneous feedback saying after every step, oh, this is the solution you should have used. The feedback is often delayed, so there might be no reward, no reward, no reward, and then eventually you get some big reward. And what mattered was the whole sequence of steps that you took to achieve that reward. And time really matters. So again, if you look at most of machine learning, with fairly large exceptions, a lot of machine learning, all the basic stuff which you've probably looked at in supervised learning and indeed unsupervised learning, the basic case is IID data. So every single step you get some independently sampled element from some distribution. Whereas in our case, what we're going to concern ourselves with is sequential data, where there's some agent that's interacting with some system, and that system has some dynamics to it that take the agent from one state into some other state, or take the system from one state into some other state through some whole sequence, and the agent has to sort of navigate its way through this whole sequence of states so as to achieve its goals. And an important aspect of that is not only is it in this sequential setup that's non-IID, but also the agent's able to influence what the next state will be. So it can take actions that actually determine what the next thing which will happen to it. So it's not that it's just, there's some weather that happens, whether the agent likes it or not, the weather might change. So that's an example of non-IID data. In this case, we have an agent that's actually able to influence the stochastic elements of the course of its future. It can change its future by behaving differently. Okay, so we've talked about these examples of what people have done with reinforcement learning. What I'd like to do is maybe just expand on some of these examples over the next sort of few slides so you get a better idea of, first of all, how we can put together this reinforcement learning framework. But most importantly, when you first look at this slide, it probably feels like these are sort of quite different examples of machine learning. So the question is, how can we build a single framework that encompasses all of these problems? And the key aspect here is that they're all examples of sequential decision making, where an agent interacts step after step. It takes actions, it receives rewards, and it sees some kind of observational state about where it is, or for example, we'll come to that in a second, but if it's a helicopter, it gets to observe it's the sensors of the helicopter telling where it is, and so forth. Okay, so these are the videos that I'm afraid I can't show you, but we saw one of them last time. Okay, so now really what we're going to work through in this lecture is really focusing on two things really. So first of all, the reinforcement learning problem, which is how we formalize this problem. But we're not going to go into the details of. So next lecture is really the main formalism, which is Markov decision processes for reinforcement learning. Here we're going to take a high-level overview of just understanding how all of these different problems can be described as reinforcement learning, and how this all breaks down and how we can understand it. And then in the next part, we're really going to look at what goes into a reinforcement learning agent. That'll be the next section. And then we'll probably stop around there. Okay, so we've talked a little bit about rewards. So let's define reward. Well, a reward is simply just a scalar feedback signal. Every single time step t, it receives some reward. And the whole of reinforcement learning is sort of premised on this quite interesting hypothesis that's sometimes called the reward hypothesis and sometimes simply called the reinforcement learning hypothesis. So called because if you believe this hypothesis, then all of reinforcement learning is justified. And if you don't, you'll always have this question in the back of your mind, well, should we be doing something else, or is this the right way to proceed? So the hypothesis is that everything which we mean by decision-making, by goal-seeking agents, by systems that have some purpose, this is for both biological, animals, it's also artificial agents, machine learning, anything where there's some system that has some purpose. The hypothesis says that all of these different goals can be described in the same way by the maximization of a single scalar reward signal. So it can always be broken down into a single scalar reward signal, which might be like a pleasure-pain signal that an animal is trying to maximize over time. So I don't expect everyone in the room to agree with this statement, but it's certainly interesting to think about, because this is really fundamental to why we study reinforcement learning, why it touches on all these fields. Because if you believe that you can formulate something like winning a game. You can formulate this as at the end of the game you get some positive reward. If you're flying a helicopter, at the end of it either crashes or achieves its destination. So once you start to understand how lots of different problems can be formulated as the maximization of an accumulation of reward signal, you might start to either agree or disagree with this statement. So I basically encourage you to, at the end, once we've seen these examples, maybe just, okay, so this is not, it's an informal homework task, is just to think this through for yourself and ask yourself whether you agree with it. Okay. And the agent's job is essentially just to maximize this cumulative reward. So that's what reinforcement learning is all about. Okay. So we talked about the helicopter a little bit, that you could get some positive reward for following the desired trajectory and negative reward for crashing. In a game, as I mentioned, you can get positive reward for winning, negative reward for losing, and probably zero reward at every step along the way. And now you simply need to maximize the cumulative reward. Every step you take, every move you make, you get the option of which move to take. You get this zero reward until the end of the game, where you either win or lose. And now you need to choose the sequence of moves that helps you win the game. If you're managing an investment portfolio, you could formulate this as a positive reward for making money. So each time you manage to bank some dollars into your bank account, this would be a positive reward. And again, this is something you want to accumulate. So it might be that you're prepared to take a loss in the short term so as to maximize your long-term gain and get more money in your bank at the end of the day. And then for a power station, you get a positive reward for producing power, a negative reward maybe for exceeding safety thresholds or reactor melting down or something. So in each of the problems, this is the problem design issue. So constructing a reward signal, this formulates the problem that our algorithm is going to try and solve. So you can think of it as there's two sides of a fence. The reward signal is part of the problem description, and the agent's job is to maximize that reward signal for whatever that problem is. So another example might be a robot, and maybe it gets some reward for going forwards and a negative reward each time it falls over. Okay. So, sequential decision making, as I've said repeatedly, the goal is to maximize this total future reward. And this is stochastic, so in fact we try to maximize the expected total future reward, because there are many different trajectories that the agent could go down. And the actions that the agent takes can have long-term consequences. There's something it might do now, which takes many, many steps before the consequences of that action are revealed. So in particular, it may not be the right strategy to maximize greedily the reward at every single time step, because a lot of the good rewards might be delayed. So it might be better to make a sacrifice to gain more long-term reward. So like a financial investment, which might take a long time to mature. Refueling a helicopter, well, what's the point in that? You lose reward, but in the long term it might prevent a crash. Or maybe if you're playing a game, you might spend some time to block your opponent, because many moves later this might give you a better chance of winning. These are all examples where in the short term it looks like you're doing something undesirable, but in the long term it helps you to gain something. Okay, so now we're going to talk about the two different parts of the reinforcement learning problem. So the agent is basically, that's the thing we're going to build. The agent is the algorithm, this is the machine that we're going to construct to try and solve the problem. Whereas the environment is basically the problem that we're trying to solve. It's the world that the agent's situated in. It's you can think of this as the helicopter or the robot's body or the game that's being played. And so basically what we have, probably a better picture, is we have these three key elements of experience. We have actions, we have observations, and we have rewards. So this brain here represents this. This is the algorithm, this is the agent, this is the thing we're trying to build. We're in control of this. Our job is to build that thing there, that brain. And this world represents the thing that the agent's situated in. So the robot and the room it's in, and everything that sits outside of the agent itself. And so basically we get this flow of information. We get the agent gets the opportunity at every single step to take an action, AT, and in return the world supplies some reward. This is the reward signal we talked about, RT, and also the world gives some indication of what's happening. So some observations, OT. So this could be something like the price of the stocks. It could be sensors of a robot. It could be all kinds of things. It could be full state information describing exactly the position of the board. It could be all kinds of things that go into it. And in return, the environment takes the next step. It receives that action, and it emits an observation and emits a scalar reward. And we'll move to more formal representations of this in the next lectures, but for now I'm just trying to give you an overview, a sort of rough feel of how this all fits together. Okay, so I really wanted to talk about the notion of state. So this is something which is bandied around quite a lot, but very rarely is actually defined precisely. So I'm actually going to try and do that here. So first of all, the agent receives some sequence of observations, actions, and rewards. This is its sort of observable experience. We can think of this as like everything it's ever seen, or the sensory motor stream. If it's a robot and it's situated in some world, you can think of this as a sensory motor stream. Or if it's an animal, it gets to see things, it gets to take actions, it gets to experience rewards. So it has this sensory motor stream, we call this the history. And what happens next depends on the history. So basically, the history determines the situation that the agent's in. Everything it's seen so far gives it information about what's going to happen next. So from the agent's point of view, this information that it's seen is what it uses to select the next action. So depending on what its sensory motor stream has been so far, its history has been, it's able to select different actions. And the environment in turn, what the environment does next also depends on this history. So the next observation and the next reward may, in general, depend on this entire history. So you can have very hard problems where, in fact, what you've just seen isn't enough to tell you about what's going to happen next. You have to know about the entire history of events so far. This is the general case. So we'll talk a little bit more about that in a second. So how do we actually deal with this in practice? Well, in general, it isn't always necessary to remember this entire sequence, everything that's ever happened to the animal or to the algorithm or to the agent over the entire history of time so far. So in general, we compress this history down to something that we call state. And state is basically the information that's used to determine what happens next. So state is sort of the set of variables, the data, the information that actually really matters to decide what's going to happen next. So from the environment's point of view, it's whatever information is used to select the next observation and the next reward. From the agent's point of view, it's whatever information is used to select the next action. And what is state? Well, formally, it's just some statistic of the history. It's just some function of this sequence of observations, actions, and rewards. So it's basically, it's some algorithm that processes what's come in, all these actions, observations, and rewards, they come in, and the agent constructs, it can build any representation of the state it wants as it goes along. I mean, this is nothing more than saying that the agent is like a program, or that there's some program that's used to convert this history into a state representation. There's some set of numbers it uses to decide what to do next. So there's different. Now, what becomes tricky is people talk about state in several different ways, and it all gets a bit confused. So I'm actually going to try and tease these apart into three very important, distinct notions of state. And people tend to use these interchangeably. So if you understand these next three slides, it will really help you, I think, understand and clarify what's going on in a lot of different problems, and understanding, really something very key to not just reinforcement learning, to a lot of other aspects of machine learning. So first of all, the environment state. So what's the environment state? Well, this, I don't know if you can see it, this is supposed to be a bunch of binary numbers that are sitting inside this world. So the environment state is basically the set of numbers that this environment is using to determine what's going to happen next. So there's some set of numbers that it's using to track what's going on, and each time an action comes in, it might update these numbers and process them in some way, and there's some piece of code maybe going on in here that sort of takes this action and changes its internal state, and then it spits out a reward back to the agent and an observation of what's going on. And the agent doesn't get to see this. This is private to the environment. This is the environment state. It's like whatever's used. So you imagine this kind of two programs sitting on a computer. One of the programs sort of represents the problem that you're running, and one of them represents the algorithm that's trying to solve this problem. And each of them might have some numbers in. And here, the environment state is basically, it's the bits of information that are determining what's going on in the environment program. This piece of code on your computer that's simulating a power station, whatever it is that you're trying to solve. And that can take many different forms. It's just whatever the environment happens to use to pick the next observation and the next reward. Now, it's not usually visible to the agent, but actually for most of this course, we're going to consider the easy case where it is visible to the agent. I just want you to be aware that that is not the normal case. And actually, when you look at these textbooks, most of them, they focus on the case where it is visible, and that's a big simplification. And you need to sort of be aware that much of the real world isn't like that. And the question is, what do you do when it's not? So And also, even if it is visible, the state that the environment uses might not be the most useful representation of state for the agent to use. It might be that that's state of the environment. You know, if this is some big complicated system, it might have a lot of irrelevant information in it. I mean, imagine it really is the world. There's some animal living in the world. Well, what's the state of the world? Well, I guess it's, you know, something like, if you're a Newtonian, it's sort of the locations of all the different atoms in the world or the universe, or however you want to frame this, most of which is completely irrelevant to the agent, and which is a very, very redundant representation, and the agent needs something more useful to work with. So that might actually be the thing which determines what happens next in the world this agent's sitting in, but the agent might still want its own more useful way to think about the world. So that's what we call agent state. So agent state is now the bunch of numbers that the agent uses to decide what it's going to do next. So the agent has some internal representation. So this is now the program that sits on your computer. This is the one we're going to write. This is what this course is concerned with. It's like, how can we make reinforcement learning algorithms to solve these problems like this? And those algorithms are going to have some, you know, it's going to be a piece of code in there that has some numbers representing what's happening. And each time a reward comes in or an observation comes in, we're going to update those numbers. You know, there might be some vector representation of state, and we're going to update that each time information comes in. And basically, whatever the agent happens to use to pick the next action is what we call state. So it's the information that we're going to use in our reinforcement learning algorithms to pick actions or to predict what's going to happen next. And in general, this can be any function of history. Okay, and then finally, there's information state. So information state, which is also called Markov state, this is a more mathematical description of state. And so this basically defines a sufficient statistic of the history for telling us everything that we might need to know about the future. So what does Markov mean? Well, a state is Markov if this property holds here. So if what happens in the next state, so if we have some state representation, so we've got some state representation ST, and that state representation is Markov, if the next state, the probability of the next state only depends on the state that we're in right now. The whole history doesn't matter. The only thing we need to remember is the state we're in right now. It's irrelevant what happened before. If we've captured all the information about the whole history in this state representation, we can throw away all this old stuff and it just doesn't matter anymore. That's what a Markov state is. So another way of putting that is that the future is independent of the past given the present. So if we have some state representation ST, then we can throw away everything that has happened from now up until then. So we've got some agent, it's seen all these observations, it's taken all these actions in the past, but the only thing it needs to remember is its current state. And if that current state satisfies the Markov property, then that's sufficient to predict everything that might happen to it in the future, as well as it could ever predict it, as well as any representation of state could predict it. So if it had remembered everything, it couldn't do any better if we have the Markov property. So an information state basically tells us that we have all useful information from the history. We've kind of captured everything. The state is a sufficient statistic. And so why do we care about this? Well, the assumption is that if we have a Markov state, that this is a good state for the agent to use. That Markov states that we've captured everything, and so that's somehow a useful representation for the agent to use. So we've done a good job of coming up with our agent state. So two examples are the environment state. So if we actually know how the environment's really generating its the next observations, the next rewards, then we know everything about the process. And so that state representation is by definition Markov. Another example of something that's actually Markov is the history itself. So the history itself contains all information from the history itself. It's just sort of tautological. So if you actually use the history itself, if the agent sort of remembers everything and uses everything that's ever seen to decide what it's going to do next, then that in itself is a Markov state representation. Can anyone think why that might not be a good idea, by the way, to do that? So it's, it seems very simple and very practical, but can anyone think why the history of everything it's ever seen might not be a useful representation for the agent to use? I know it's sort of early days in this course, but it's good to just get some feedback, keep you on your toes, make sure you're all awake. By the way, I'd like this to be interactive in general as a course, so please feel free to stop me and interrupt and ask questions at various times.
Unbounded, size issues?
Yeah, so it's, this thing very quickly can grow out of hand. I mean, as the number of possible histories that the agent can see is exponential in the length of this history. And so if the agent's going to start to use this history, if it's going to use the history to decide what to do next, naively, if it's making a map that goes from history to next action, this map is going to have to be very large. It's going to have to consider an exponential number of distinct histories to decide what to do next. So typically, we try and construct some more useful state representation. Okay. So let's try and make this a bit more concrete, bring things a bit more down to earth again. So, okay, I want you guys to be this rat here. So we've got a rat. You're sitting in some experiment here, and I just want to give you a sense of what it means to be a reinforcement learning algorithm. Okay, so I'm going to show you sort of two examples of what's happened to this rat before, and then you need to decide what's going to happen in the next sequence. So the first time, there's this rat here, and it's sitting. It's in some environment. So you're the rat. You're the brain in my diagram earlier. And first of all, you see a light come on. Then you do nothing. You see a light come on, and then you pull a lever. You hear a bell, and then you get zapped by this horrible electric shock. Okay? Right. So that's the first sort of sequence of experience. The second sequence of experience goes like this. So you hear a bell, then you do nothing, the light comes on, then you pull a lever, then you pull a lever again, and then you get this nice delicious piece of cheese. Okay? So now, the question is, what happens in this sequence? So you pull the lever, you see a light, you pull the lever, you hear a bell. So I want everyone to decide on something. So put your hand up if you think that the rat will get an electric shock next. Okay, you're all pretty nasty, look at that. Most of you think it will get an electric shock. And how many of you think it will get a slice of delicious cheese? Okay, no one. Okay, so let's think about this for a minute. On what basis have you decided this? Well, it all depends on what the state representation that you're using is. So if the agent state that you're using, the sort of representation of what's going on in this sequence, if you sort of look at this sequence and pick out that the important thing about this sequence is the last three items in the sequence, well, then you're all right. That if the state representation is the last three things that you've seen, well, clearly there was a light, a lever, and then a bell, and you got an electric shock in the first one, and here there's a light, lever, bell, so you'd expect there probably to be an electric shock. But that's only one construction of agent state from this sequence. What if we were instead counting the number of lights, bells, and levers? So that seems a perfectly reasonable thing to do as well. It's like, well, maybe the only thing that matters is how many times you pull the lever. Well, in the first example, we only pulled the lever once, so we got shock. But here we pulled it twice, so we got the delicious cheese. So maybe all the rat needs to do was just pull the lever twice, and it would have got another delicious piece of cheese. And what if the agent state is the complete sequence? Well, then we simply don't know. We haven't seen this complete sequence before. We haven't seen this complete sequence where there was a lever, then a light, then a lever, then a bell. We've only seen sort of somewhat similar sequences. So you've all generalized. You've all constructed a representation of state when you all answered this question a certain way. You picked a representation of state, this first one, the last three items in the sequence. I just really want to point out there are many choices of how to represent state, and this is a very big question in general. In fact, it's probably the hardest unsolved problem for reinforcement learning is how to do this properly. Okay, so fully observable environments. What's full observability? So in a fully observable environment, an agent can directly observe the environment state. So here I've superscripted the state st by either A for the agent state or E for the environment state. And the special thing about full observability is that all these different definitions of state, they all sort of collapse to the same thing. So if the agent gets to see the state that the environment is using, like we're playing a game and the state of the board is whatever position the pieces are in, and the agent gets to see that state of the game, or if it's in a factory and all the things that make this factory run are exposed to our algorithm, we get to see everything about that factory, it's fully observable. The agent state is the same as the environment state, and therefore the same as the information state. It knows everything about this system, and therefore it's has all the information required to predict what will happen next. Now, formally, this particular case, which we'll do in more detail, this is known as essentially a Markov decision process with some details. And that's going to be the topic of the next lecture. And the majority of this course, and indeed both of these textbooks, as I mentioned, is concerned with the fully observable case. So what's the other case? Well, the other case is partial observability. So this is where the agent only indirectly observes the environment state. So like a robot with camera vision, maybe it doesn't have a GPS sensor, so it has to figure out from its visual input where its absolute location is. Or a trading agent, maybe it only gets to observe its current prices. Or a poker playing agent, it only gets to see its own hands and hands on the table. It doesn't get to see the opponent's hands and has to decide what to do next. And so now, sorry, this should say not equal to, but the agent state is not equal to the environment state. So this is known as a POMDP, a partially observable Markov decision process, which we'll touch on briefly, but we won't do as much detail. And in this case, as I mentioned, the agent has to construct its own state representation, has to decide what to remember from the history and how to process that information so as to kind of record all the useful information and construct something useful to work with. But there is always this one simple choice that I think is often overlooked. And the simplest choice is this point we made earlier, that it can always use the complete history. I mean, this is something it's observed. It's seen the complete history. So if it uses this as a state representation, yes, there's some drawbacks. This is a very large, unwieldy representation. But this is actually the simplest choice that basically brings us back. You can actually do everything as a Markov decision process again if you do this. But that's sort of a detail that it's good to have as a bullet point when you ever come back to these slides. Okay. Okay, so what goes inside an agent when we're actually now looking at building? We want to build something. This is going to be there'll be some theory, but there's also going to be some algorithms in this course. I want you to understand how to build reinforcement learning agents. And so what goes inside? What are the components? What are the things we're trying to build? Well, I think this is actually, in my opinion, the best way to understand, to categorize reinforcement learning is by dividing up a taxonomy of reinforcement learning by the components which are actually used inside that agent. And that taxonomy includes these following components. So there's something called a policy. So what's the policy? Well, the policy is the agent's behavior. It's basically the thing that determines, given some state, what the agent's going to do next. There's a value function, which is sort of how good is each state and or action. And there's a model, which is the agent's representation of the environment. And an RL agent in general can have any combination of these three components, which we'll come to in a minute. But first, let's understand what those three are, just to some rough level of detail. So what's a policy? Well, it's a map from state to action. It can be stochastic. So it's basically a policy we call pi, is basically the probability of picking an action given some state. So the agent it sees a state, and now it can pick which action it's going to do next, or a distribution over actions that depends on that state. And stochastic policies can be very useful. For example, if you're playing cards again, just picking the poker example, you probably don't want to pick the same thing every time because you won't have an optimal strategy then. Okay, a value function. This is the second major component. What's a value function? Well, it's a prediction. It's a prediction about future reward. So it's a prediction of the total future reward that the agent expects to see following its current behavior, following a particular policy. And it's used to evaluate the goodness or badness of states. And if it can evaluate the goodness or badness of states, it can use the value functions to decide which action to pick. And there's different types of value function. Here I've just shown, this is the value function for a typical Markov reward process or something. But roughly speaking, it's just the expected total sum reward given that the agent is going to start in the state that we care about. So if you dump the agent down in a particular state, how much reward would we expect it to get from that state onwards? And that tells us something about how good that state is. Do we really want the agent to be in that state or in another state? Well, let's look at the value function. And if it's going to get more reward from one state than another state, well, then it should pick actions that take it to the state with a higher value. So that's sort of the key to a lot of reinforcement learning algorithms, to use the value function to determine its strategy for action selection. Okay, the third major component is the model. So what's a model? Well, it's basically, it's the thing which predicts what the environment will do next. So one way to understand this, sorry, put the picture in directly. If we go back to our familiar picture, the agent is basically, the model is basically the agent's own representation of what this thing here looks like. So it doesn't know the true environment, but it can build its own representation of what's going on here. It can start to learn this thing. It can start to learn what the environment's going to do. It can start to learn how the factory behaves, or it can start to learn what the rules of the situation it's in is, or it can start to learn how a trading system behaves, or whatever it is. So It predicts what the environment will do next. So there's two parts to that. It needs to be able to predict both of those arrows that came out of the environment. So it needs to be able to predict the next state, and it needs to be able to predict the next immediate reward. So this is different to the value function. The value function predicted long-term reward, like the accumulated reward that the agent's going to get from then onwards, starting at some state. Whereas the model just predicts what's going to happen next. So it has these two parts, which typically look something like this. We'll talk about this in more detail next lecture. This is for a Markov decision process, what the model looks like. But basically, it always has these two parts, something which tells it basically what's going to happen next, given the state it's in now, and the action it picks. So that's what we're conditioning on here. S is this current state, A is the action that the agent selects, and we've got a prediction about what state we'll end up in next and how much reward we'll get. Okay, I think I might start. So here's a very simple example of reinforcement learning that I think is helpful. The only thing that's slightly misleading about it is that the maze, because we all think we know how mazes work, we've all got sort of our own understanding of what mazes are. So you sort of need to let go of that understanding. I think, imagine you're some kind of algorithm that's never seen a maze before and doesn't know what the maze is going to look like. And that's really the reinforcement learning case. The problem could be anything, it just happens to be that it's a maze here, and that some start and some goal. And how could we formulate this? Well, we could formulate this by saying, for example, there's a reward of -1 per time step. So taking a longer path is bad. The problem stops when it reaches the goal. So if it reaches the goal in the shortest possible time, then the agent's done as well as it could in this problem. It can move north, east, south, or west. And the states, in this case, are just the agent's location in this maze. So this is sort of making all of these concepts concrete, the rewards, the actions, the states. This is fully observable, so states and observations are interchangeable here. Okay, so now let's talk about these components. What do they actually look like? So first of all, we might have something, well, a policy. What's a policy? A policy is basically, this is the behavior that the agent has. So this is like a visual representation of one possible policy that the agent might have, which is in fact the optimal policy in this case. So for each state that the agent could be in, there's an arrow telling it how to behave. So this is a deterministic policy. You could also have stochastic policies where you have a distribution over these arrows. And so the policy guides the agent from the start to the goal. But if it's perturbed by some random force, let's say this is a noisy maze where with some probability it gets pushed off course, if it gets perturbed, it still knows where to go. So this policy actually works in situations where there's sort of, where you need to do closed loop planning rather than just open loop planning. So if it gets pushed off its course, it still knows what to do. It covers all possible scenarios, all situations it might find itself in. Okay, what does a value function look like? So the value function, remember, is the thing that says how good or bad is a state. So the states here are the different places in the maze, and they're a prediction of how much reward you would get from that state. So clearly, if you're here, well, you're just by the goal, so you can get to the goal in one step, so your prediction of value would be -1. Here, you're just 2 steps away, so your value is -2, and so forth, all the way back. And again, this is something which maps every single state to a value, even the states which aren't on the sort of optimal route to the goal. So this is a value function. This is a simple example of value function. Well, what about the model? What does the model look like? Well, there's 2 parts to the model, remember. There's the reward part, which tells us how much reward it's going to get at the next state, and there's the sort of state transition part, saying what state will you see next. So we're trying to model this environment. And so the agent has its own internal model. So it might be that one example of a model might look something like this, where maybe it doesn't know about the whole maze yet, it's only explored some of this maze. So maybe this is the part of the maze it's seen. So these black and white sort of squares here indicate what the agent thinks its world looks like. So it's got some beliefs about the world. It thinks the world looks like this, that's its model. And it believes that every single step it's going to get a -1 reward. So this -1 indicates the immediate reward it's going to get. So this is sort of just trying to make intuitive these concepts of value, function, policy, model. So the dynamics here are very straightforward. It just understands that if it moves around this maze, it will get from state to state. Okay. Right. So now we understand these different components, we can start to put them together in different ways, and this is going to give us our taxonomy for reinforcement learning agents. So first of all, we can have something called value-based agents. So we have something, value-based reinforcement learning basically means agents that use a value function to decide what to do next. So they store a value function, they have some kind of value function, they're going to build some representation of say, this maze. They're going to store something like this in memory, and they're going to use this directly to decide what to do next. So they've got this in memory. Once you have this in memory, if you're in some location like that -15 state there, you know exactly where to go, because you would choose to go to the -14 rather than the -16. So once you've got the value function, you can directly pick actions. So in some sense, the policy is implicit, or the policy is not directly stored itself. So this is what we mean by value-based reinforcement learning. So we store a value function, we don't store a policy. Alternatively, we can do policy-based reinforcement learning. We'll have a lecture on this later on in the course. In the policy-based reinforcement learning, we don't store a value function, and instead, we directly store the policy. So we work directly in policy space, and you can imagine doing something like policy search. A very naive example of this would be, imagine you've got some genetic algorithm that's just searching for a good policy that achieves good results in your problem. So you just find a policy, you blindly search over all different policies until you find one that makes your power station run efficiently. And then we have what's called actor-critic algorithms. And these have both a policy and a value function. And the terminology actor-critic simply means that there's an actor, this is the policy, this is the thing which does stuff, so it acts in the world. And there's something which is called the critic, which basically is like, imagine there's an agent and it's trying to criticize all the different states it could end up with. So the critic is the value function, that's the part that's evaluating. So it's value-based, policy-based. If you combine them together, you get actor-critic. And then for all of these cases, we can have what's called model-free or model-based reinforcement learning. So model-free basically means the agent never tries to construct a model explicitly of how the world works. Instead, it works directly with its policy. It just gets feedback about how well it's doing, and it adjusts its policy directly from that feedback, without ever trying to build a representation of how the world works. So it never tries to explicitly represent the dynamics of the weather system it's in, or it never tries to explicitly model how trends in the financial markets change over time. Instead, it just works directly with the policy and the value function. In contrast, model-based reinforcement learning methods explicitly construct some model of both the reward and the transition, or the dynamics of the problem it's trying to solve. So model-based reinforcement learning constructs some model of how the problem it's in works. So it makes a guess, so like in this case here, where it builds some guess as to how the problem it's in works, and then it solves for that guess. So that's model-based reinforcement learning. Okay, now I think we've got time for this. Is that correct? I'll just check. So within the broad framework of reinforcement learning, there are some important problems that we need to address as well. And so I just wanted to give a flavor as to some of those problems that we need to think about, because these will be major topics within the course as we go along. And so two of the most fundamental problems that we need to think about are what's called reinforcement learning and planning. So this is why this is learning and planning. There's sort of two different problem setups that are both very important, and we'll talk about them both. So what's the distinction between them? So in reinforcement learning, the environment is unknown. The agent doesn't know the problem it's trying to solve. No one tells it what the rules of the game are. No one tells it exactly how the stock market's going to work. No one tells it what the dynamics of the power station are, or no one tells it how the weather systems move around. It has to, if it's going to figure that out, it has to figure it out itself. So the agent just interacts with that environment, gets more and more data, and using that data, it improves its policy, either by building a model or by in a model-free way. In contrast, the planning problem is where the model is given. So the agent knows the environment. It's assumed to have perfect knowledge of its environment. So it knows exactly the problem that it's trying to solve. So there's no learning required, but it may still be a very hard problem to figure out the optimal way to solve this. So it's like, this is much more like our way we think about solving a maze. Typically you imagine that you know the whole maze, the maze is put in front of you, but there's still some planning required to find the right solution to that maze. Or if someone shows you a Sudoku, and tells you the rules, you know how to proceed in this problem, but it's still a hard problem to actually find the optimal solution. And this is also true for more intuitive things, like maybe you're playing a sport and your planning might be that you know exactly how the dynamics of the tennis ball are going to operate and how the movements of your arm are going to affect the tennis racket. But the planning problem is still there. Even if you know exactly how all these dynamics operate, there's still a big planning problem, which is how to figure out exactly where to strike that ball so that it will go over the net in exactly the right trajectory and cause your opponent problems, and maybe they'll hit it back in a particular way. So even if you know exactly how the environment works, the planning problem can still be challenging. So to do planning, the agent basically performs computations with this perfect model of the environment, or whatever its model is. If it has some model, we're just basically trying to do computations with that model without any real interactions. It's like it has some model that's given, it's not really interacting, it's just figuring out, it's like thinking, it's kind of figuring out through a process of thought or cognition, it's trying to figure out what its action should be, and thereby improving its policy. So, if you were really, I don't want to take this too literally, but some people might argue that what we mean by things like deliberation, reasoning, introspection, pondering, thought, and search, all of these things can be thought of as a kind of planning. These are planning processes where some agent is trying to reason about what it should do next by imagining how it might interact with some model that is given about how its world works. Okay, so let's do it the other way around. So here's another maze example. Sorry that's so mazy. The rest of the course will have non-mazy examples, and there were some videos that we missed, so I have to bring those in. So here's the reinforcement learning problem, first of all. So imagine now you're not told what the maze is. You don't really even know necessarily that if you try to go south, that you'll necessarily end up going south. There might be noise, you might be pushed away, and you just need to figure out what the best thing to do is. So here's an example of a trajectory that you start, you take some actions, and you end up going in this trajectory, and at the end of this trajectory, you get a reward of minus 117. And then you get to go again, you get to take some other trajectory, and taking account of the noise and all the actions that you can take this longer trajectory, but maybe the reward actually here ends up being, say, minus 38 because you pick up some juicy thing along the way. And so the question is, what should the agent's policy be after these two episodes? And so that's the reinforcement learning problem. It proceeds by trial and error. It feels a bit more like this, that you're kind of, you don't really know what the maze looks like, you're just trying to figure out by trial and error, after seeing examples of trajectories, what to do next. And so now you might have some idea at the beginning of this maze, you probably take something more like this route over here, because it ended up with a reward signal that was minus 38 there. So reinforcement learning is kind of like trial and error learning. Oh, sorry, and I wanted to do the planning example next. Planning feels more like this, where the model is fully known. So now the agent knows, well, it's in some model that looks like this, how should it solve it? And so so planning basically is, you're presented with this thing, what should you do? Now the agent goes away, it does some search, it figures it out, it imagines how it might interact with this model so as to solve this maze. Okay. So one more problem that we need to deal with in reinforcement learning. This is the exploration and exploitation dilemma. So reinforcement learning is kind of, it's like trial and error learning. You get to, the agent, it tries out some actions, it takes some sequences of actions, it sees how those sequences do, whether they lead to good rewards or bad rewards, and it gets to try and do better over time as it gets more experience. And the goal is for the agent to discover a good policy, a good way to behave. And it gets to do that by accumulating experiences of the environment. But what's key here is that it wants to do that without losing too much reward along the way. So it's going to be interacting with its environment, and it wants to find out what's going on in that environment, but at the same time it wants to make sure that it's actually not falling off cliffs and crashing helicopters and losing tons of money on the stock market and blowing up power stations. It wants to figure out how to behave optimally without doing any of these bad things. So this is the exploration and exploitation dilemma. It has to balance these two aspects, and this is really fundamental. It's something which really is central to reinforcement learning and doesn't really occur so much elsewhere in machine learning. So exploration basically means trying to find out more information about the environment, trying to understand how the environment works, trying to try new actions that haven't been tried before, new parts of the state space that haven't been seen before, so exploring things. Whereas exploitation means, well, you've already seen some stuff, how do you exploit that known information so as to maximize the reward? And in general, these have to be traded off very carefully to get optimal performance. So some examples might be, so these are all informal examples, but imagine you're so these are sort of down-to-earth examples we can all imagine, but imagine you're going to some restaurant. Well, do you go to your favorite restaurant? That's exploitation. You know that you like this restaurant, so you just go there. Or do you try a new restaurant? That's exploration, and hope that you find a restaurant you like even more than one you've been to before. So if you never explore, you'll end up stuck with your local cafe at the end of your road, which is the first thing you try, because you think, well, that one's okay, so I can always just keep going there. But you want to continue to explore so that you can potentially find something better and get more long-term reward eventually. Another example, this is very widely used, big sort of practical application of exploration-exploitation trade-offs is for online banner advertisements on the internet. And so here, the problem is to show an advert to a user, and you want to basically make sure that the users are actually going to click on the adverts and care about these adverts. You want to show them something they're maybe can have some chance of clicking on. So exploitation here would be to just show the most successful advert, the one that's had the highest click rate so far. But if you do that, if you always just exploit, you won't find out if maybe some of your other potential banners that you could show to them, these other adverts, might be more popular. So you need to show a different advert every now and then to find out if actually maybe trends have changed and maybe people will be more interested in some other advertisement. Another practical example would be oil drilling. So exploitation here would be to say, okay, you can drill for all these different places, and we know where maybe there's some oil around. There's not so much left these anymore, but there's some places where there is still oil, so you could just drill and drill there. Or should you drill a new location where you're just trying to gather information and find out if there's potentially some oil down there. So that would be exploration, rather than just exploiting and drilling at the places where you know that there's been oil before. And game playing, exploitation would be playing the move you believe is best. So whereas exploration would be something like playing an experimental move. So it might be that you've kind of figured out some rough strategy of how to play this game against a particular opponent. But occasionally you might like to try something crazy just to see how they'll react to that, and maybe that crazy way of doing things will actually really sort of unsettle them and you'll figure out a better way to play. So all of these are examples where you need to balance the exploration and exploitation trade-off successfully. Okay, so I think this might be the final sort of sub-problem within reinforcement learning I want to talk about. And it's about prediction and control. And I know there's been a lot of different terminology thrown in here in this lecture, but this is the overview, and we'll focus on particular pieces of this bit by bit. And I think it's really good just to get some overview of how it all fits together. So prediction and control, this is another big choice of what are we actually trying to do. So what's prediction? Well, prediction means trying to predict something about the future. In particular, in reinforcement learning, what we care about is a particular prediction problem, which is to evaluate the future, to predict how much reward the agent will see in the future. So if it's going to behave in some way, if it's going to follow a particular policy, how much reward will it get following that policy? That's the prediction problem. So that's prediction, sometimes it's called policy evaluation. So a lot of reinforcement learning focuses on just prediction, figuring out if you're going to behave in a particular way, how much reward will you get? And if you know that, well, then maybe you can improve your way to behave, because you can evaluate each of those different ways to behave. So control is not just about prediction, it's about optimization. It's about finding the best possible policy. So now this is what we really care about ultimately, is we want to know, well, what's the best way to control our power station so as to maximize throughput? What's the best way to fly a helicopter so as to not crash and reach our desired trajectory? And so this is really about optimizing the future reward that we're going to see. So we've got some expected reward, and we want to maximize that expected reward. And this is what we call control. And so when if you ever hear about control theory is really about, a lot of it's about exactly this problem, optimizing the future, finding the best policy. So if you have some dynamical system, you might want to figure out, well, what's the optimal way to control your submarine so as to minimize the amount of fuel it expends to get to its particular desired location in some known system. So that's the control problem. So prediction and control, and it turns out that a lot of reinforcement learning, what we can do is to solve the control problem, we first solve the prediction problem. So prediction becomes like a sub-problem that's used to achieve control. So here's one example. We'll actually go through this example in more detail later, but just to give you some flavor, this is a grid world here, so we'll use some grid worlds just to they're a little bit like mazes with special rules, if you like, and it just helps gain some intuition. And the question here is, if you're going to behave in a particular way, so we have this problem here, where every time you go to this square marked by A, the agent gets teleported to A prime and gets a +10 reward. And every time it goes to B, it gets teleported to B prime. And any other action it takes, it gets a -1 reward. And it can move north, east, south, or west. So the question is, if you were to behave in a particular way, in other words, if you were to behave, for example, uniform randomly, what would the value function be here? That's the prediction problem. How much reward will the agent get long term? What's its expected cumulative reward? If it just moves around randomly through this whole system, how much reward is it going to get starting from any state? That's the prediction problem. And this is the answer to the prediction problem over here. So you can see that if you're close to this nice A state here, and you're moving around randomly, then you expect to get a reasonable amount of reward. But if you're a long way away, then you're not going to get as much reward. So that's the prediction problem. The control problem is optimization, it's maximization. We want to maximize over all different policies now. We want to find the optimal way to behave. And so one way to think of this is what's the maximum amount of cumulative reward that the agent can receive if we optimize over all possible policies. In other words, this is what we'll call the optimal policy. And so we'll have something which we call the optimal value function. This should be pi star, I'm not sure why it's come up as a not equal to star. And so now you can see that the agent's able to get a lot more reward because it's able to decide what to do. And so it can actually move towards A now. And you can see this is the optimal policy over here. So control basically means finding this optimal policy over here, which is the best way to behave. So if it's close to A, it wants to move to A. And if it's stuck in this corner in the wrong direction, it wants to get out of there. And so these are the prediction and control aspects of reinforcement learning. Okay, so now we're in a position, just to finish up, to sort of go over the course outline and hopefully have some idea what I'm talking about with this course outline. That was the goal, remember. So I hope we've got to the point where we can understand what the course is going to be about. So we've had lecture 1, so tick, that one's done. So next lecture, we'll talk about Markov decision processes. So this is basically the major formalism for reinforcement learning where we assume that the environment is fully observable. So we're going to spend a whole lecture really trying to understand Markov decision processes. There are very large books written about this subject. We're really going to try and focus on some of the core concepts of understanding how to basically understanding what value functions are and how they relate to themselves. There's a very elegant theory about Markov decision processes. So we can try and understand Markov decision processes because if we can understand those, almost all other aspects of reinforcement learning can be formalized as MVPs. So if you get that part of the theory, then everything else will sort of fall into place around that. So that's sort of the description of the problem. Lecture 3 will be algorithms for solving these Markov decision processes. So planning by dynamic programming. So this is the first major class of algorithms for solving these methods, and these are going to be value-based reinforcement learning methods, but just doing planning. Sorry, we're not going to be doing any learning of how the environment works. So lecture 3 is where we assume that the environment is known and the agent is just trying to plan a solution, trying to figure out its way to solve the problem. In the lectures 4 and 5, we're going to move to model-free algorithms. So this is where the agent isn't told anything about its environment and has to figure out from scratch how to solve this problem. It's a bit more like the rat with the bells and the lights. It just needs to, it's thrown into this world and it needs to figure out what to do. And first of all, we're going to focus, we'll spend the whole lecture just dealing with prediction and how we can predict what's going to happen for a given policy, and then we'll use that in the subsequent lecture to come up with model-free control algorithms that really, so this is, this is really now, we'll get all the way to these are proper solutions to the full reinforcement learning problem of how to come up with the optimal policy and the optimal value function. I know lecture 4 and 5 are really bad, so you can see it the wrong way. Okay. No, they'll actually be good. Okay, and then part 2 will be more about reinforcement learning in practice. So once we've got these sorts of fundamental ideas under our belts, how can we use them? How can we extend them? How can we do things that are a little bit more sophisticated? And so here we'll start to look at value function approximation. So the key issue here is that lectures 1 to 5, we're going to assume that we have like a simple problem that we can fit in memory and that we can represent every single state that the agent might come to separately. So we're basically, parts 1 to 5, we're going to imagine that the problem we're solving is small. And in this 6th lecture here, part 2.1, that's basically where we'll start to open the box up a bit and say, well, what if we're trying to solve a big problem? What do we do? And the answer is that you start to need to use function approximators. You can't just represent the value of each state separately or your policy for each state distinctly. You need to start to approximate these. And so that first lecture will be how to do that in a value-based way, and the second lecture will be how to do that in a policy-based way. So if we're searching directly through policy space, there'll be a lecture which is entirely devoted to solving these larger problems using policy-based methods, which can also be very successful. The next lecture will be how to integrate both reinforcement learning and planning together. So all the other lectures up to this point will sort of deal with one of those problems separately, but you can actually get a lot further by combining them both, and there's a lot of really nice algorithms that both learn and plan, and we'll start to understand that these sort of, they're almost like two flip sides of the same coin, that you can use the same algorithms to both learn and plan. Then we'll have a lecture covering this exploration and exploitation dilemma and methods for solving that, and we'll focus particularly on a very well-known sort of simple setup for reinforcement learning known as the multi-Unbounded, which is where a lot of the good work on exploration and exploitation has been done. It provides a really good way to understand these things. It's a bit like the online banner advertisement setup I was discussing earlier, which things should you pick up. And finally, we'll have a case study which will basically use most of the algorithms we've developed up to this point in a case study to show really how state-of-the-art performance has been achieved in board games. So this is actually interesting because in reinforcement learning, it turns out that if you look across the major board games where people have written computer programs for them, reinforcement learning algorithms have achieved human world champion in level of performance in almost all of those games. There's only some minor exceptions where other machine learning methods have done better than reinforcement learning. And on the whole, these reinforcement learning methods have been remarkably successful. And so I'd like to really just cover why this is the case, what methods have worked well, and understand how to bring together, in particular, some of these methods from earlier on and show how that works in practice. Okay, so next time, lecture 2, Markov decision processes. So sorry it was so late to get going today. Thanks for everything.